Questa è una bella carica per fare la... Facendo la stessa faccia delle andre riprese. We are ready.
This is just a list of some general benefits of SR implementation, but there are some of them that are specific for a software DVB-T receiver. For example, an easy upgrade to further DVB-T standard evolution, or the availability of a fully controllable, computer monitoring receiver chain intended for signal development and testing on bench and on field. All these are expressed in our proof of concept, real-time, fully software SR-DVB-T receiver on a general purpose processor. The software section of our project lives in a new SDR framework that we call New Radio. It was developed at the DSP Cola and conceived in order to minimize layers of abstraction. It provides a single programming language implementation in which C++ is responsible for both the functional block implementation and their interconnection. It provides also within block and extra block multi-threading support with thread synchronization capabilities and accurate fault control. The communication toward and from USRP is obtained by linking to the libUSRP external C++ library. The other section of the project is the well-known USRP board, and I think that I can skip the technical specification of this board. I say that for the receiving side, we have the daughter board used is a WBX receiver, while for the transmitting one, the daughter board is a Flex 900. This is the figure of our SR-DVB receiver chain. The first two blocks, RF from then ADC conversion, are provided by USRP, while the remaining functional blocks, except the FFT block, was implemented from scratch at the DSP Cola. And we can see all the receiver chain as the concatenation, the composition of two signal processing chains, the synchronization chain and channel estimation equalization functions from FDM sync chain to channel equalization, and the channel decoding subsystem from frame adaptation to transfer stream extraction. The first part of the receiver, this is the zoom of the first part, has a major impact on sensitivity and the goodness of our receiver. We use two estimation algorithms in this part. The first is the Borderson timing and fractional frequency offset estimation as a fraction of the intercarrier spacing, and the energy-based integer frequency offset estimation as a multiple of the intercarrier spacing. The first of these algorithms is a maximum likelihood estimation, which exploits the inner redundancy contained in each cyclic prefix of the OFDM symbol. Then we have the minimum channel estimation and the channel equalization, in which we apply the zero forcing technique. All the renewal of the estimation is controlled by a tricking algorithm made on a field state totem, which is based is threshold based and based on a matrix that we extract from the TPS subcarriers at the output of the equalization block. TPS subcarrier are a special subcarrier of the DVB-T standard in which are transmitted the parameters of the signal and are in a fixed position on the spectrum. This is the second part of our receiver. This is the channel decoding subsystem, where the block decoder, this bit-solomon decoder, and the VTERB decoder. This part accounts for the majority of the computational cost, and in particular, VTERB decoder is the computational EVIS block of the receiver chain. Application of the main technique yields VTERB decoder throughput of about 18 megabits per second on one core. while causing no loss in its error correction capabilities. SR-DVB was tested and developed at SR with a signal transmitted by SR-DVB, which is a real-time, fully software modulator presented 2 years ago here in Castello by Vincenzo Pellegrini. And this is the specifications of this signal. We have a transmission mode with 2K with 2048 subcarriers on a channel bandwidth of 7 MHz at a sampling rate of 8 megasamples per second and a sticky prefix length of 1/4. The constellation used is the N16 QAM with a convolution encoding rate of 2/3. All this yielding to a useful bit rate of 11.612 megabit per second. And on this PC, and we show after, we have a processor which is an off-the-shelf processor. It is an Intel Q9400 and a memory resource of 4 GB RAM DDR2 on an operating system which is Fedora 12. With this configuration, we obtain a real-time demodulation by absorbing less than 50% of the available computational resources. And now, we try to show you SR-DVB at work with my colleague Vincenzo Pellegrini that will guide that demo. And then we conclude our presentation by describing the enabler technology of SR-DVB, which we call memory accelerator.